So, yeah, good afternoon, everyone. Today I'll be speaking on the topic time travel. So, for my story on time travel, we need to know a few concepts first. So, the Albert Einstein, one of the most famous scientists of the 20th century, invented a theory or probably discovered the theory of special relativity. So, we're going to use a part of special relativity called as time dilation. Time dilation refers to the slowing down of a clock in different environment. There are two types of time dilation: gravitational and kinetic. In gravitational time dilation, when we are in the surroundings of a gravitating mass, say that we are in the surrounding of sun or probably a higher gravitating mass like a black hole. When we are near a black hole, time slows down for us. So as the force of gravity in our environment increases, time passes at a slower rate for us. This is the concept of gravitational time dilation. So if there is a mass that is closer to a black hole, and if there is a mass that is farther away from a black hole, time will pass at a different rate for them. But both of them will feel time to pass at the same rate. So it is a tricky concept to grasp because they both will feel time to pass at a normal rate. The seconds will be the same, the minutes will be the same, the hours will be the same. But if you see both the persons at a relative frame, let's say that I'm on Earth and they're near a black hole and they are at different distances from a black hole. So when I observe them both from Earth, so I'll see the time passing at a different rate for them. So for the person that is further away from a black hole, time will pass at a faster rate because the gravitational force is less there. For a person that is near a black hole, time will pass at a slower rate. So this is the concept of gravitational time dilation. Gravitational time dilation has very intriguing applications which can be used. So for time travel, let us consider a story. So let's say that just a second. Yeah, the screen is visible, right?
Siddharth, are you presenting a static picture?
Yeah.
Okay.
Then it's visible.
Yes, it is.
Oh, okay. So let's consider this story. It's kind of taken from the movie Interstellar. So let's say that the research team finds a black hole at the edges of a solar system near the planet Saturn, and from there they analyze and take up data, and they find that on the other side of the wormhole there is a black hole. So a wormhole is anything that is a portal in space-time. So a wormhole is like teleportation. So if you enter a wormhole, you'll end up in a different point in space and time. A wormhole is basically a portal through space and time, which you can use to travel further distance in the universe without actually going through them. You can imagine that there are a lot used in sci-fi movies as teleportation, as portals. So that is a wormhole. So let's say our research team on Earth finds a wormhole near Saturn. They observe the wormhole and they find that on the other side of the wormhole there is a black hole. They observe the black hole and they send a research team to closely observe it. So let's say the research team consists of two of my friends, Harsh and Harshit, for example. They both travel through the wormhole and they reach the black hole. When they reach the black hole, Harshit decides to take the smaller ship and move closer to the black hole. For example, if you can see from the picture, imagine Harsh to be on the larger spaceship that is further away from the black hole, and imagine Harshit to be on the circular planet, and he goes to the planet to observe the conditions if they're vital for survival or not. Right. So imagine that Harsh is back on the spaceship, and Harshit goes closer to the black hole in order to observe it. Harshit stays there for a few hours, collects data, and then returns back to the spaceship. When he returns back to the spaceship, he finds Harsh furious. And as soon as he enters the spaceship, Harsh beats him up for no reason. After they're both tired, they start to talk. Harshit says that he's just been gone for a few hours. But for Harsh, many years had passed. Harshit had gone for a few hours, and Harsh says that he had been gone for 4 whole years. So this is the magic of time dilation, because both of them experienced time to pass at the same rate. Harshit experienced time to pass at the same rate. He collected the data and he came back in a few hours. But for Harsh, 4 years had passed. So he had been waiting 4 years for Harshit to come back to the spaceship. So that's why they had the fight, and that's not even the most intriguing part. When they both fight and they have no clue what happened, they decide to go back to Earth. When they reach Earth, they find skyscrapers all over the place and flying cars. On what intrigues them is the date on one of the buildings. They were 100 years into the future. So for Harsh and Harshit were both at a different distance from a black hole, but they were still near a black hole. Near a black hole, gravity is very high. So they were both experiencing time dilation with respect to each other and also with respect to the people on Earth. people on Earth are at a lower gravitational field, the gravitational field of the sun, which is much less than a black hole. So when they return back to the Earth, the people of the Earth had were 100 years into the future. So 100 years had passed for the people, us on Earth. 4 years had passed for Harsh, and a few hours had only passed for Harsh. So this is kind of like time travel, but this is not the most intriguing and the most possible way, as we cannot find a black hole near us. So there's a different type of time dilation, which is called as kinetic time dilation. In gravitational time dilation, it was that if we are near a black hole, that means time will pass slowly for us. That if we are near a gravitational field, time will pass slowly for us. Something like this happens in the kinetic time dilation. Kinetic time dilation states that if you are moving at a very high speed, time will pass slowly for you. It is not observed at very low speeds like the speed of a car, the speed of a jet, or even the speed of rockets. It is observed when you approach the speed of light. So as you increase your speed, as you accelerate, time starts to pass slowly for you. So for example, say a spacecraft is moving at 90% speed of the light. So time will pass slowly for the people in that spacecraft. This also has many intriguing applications in the field of space-time. All right, so just a second.
You must ask them if they have any questions.
Yes, ma'am, I will do so at the end. Yeah. For examples, this has many intriguing applications. For example, there are few particles called as muons. They're subatomic particles which constantly bombard the upper atmosphere. They're found in cosmic radiations. So a muon has a lifetime of about 2.2 microseconds, and they travel at the speed 99% the speed of light. So if you try to map the distance, for example, we have learned the formula that distance is equal to speed into time, or time is equal to speed upon distance. Right. So if you input the values of the speed of the muon, 99.99% the speed of the light, and then you input the distance from the atmosphere to the Earth, the time that would be taken to reach the surface of the Earth is greater than the lifetime of muons. That means they can't reach the surface of the Earth within their lifetime. But still, we have muons, thousands, millions of muons hitting each second at observatories and everything. So how can they reach the surface of the Earth if they can't even live that long? So this is also due to kinetic time dilations. As they're traveling at 99.99% speed of the light, time slows down for them a bit. So they have a lifetime of 2.2 microseconds. They live that lifetime only. But for us on Earth, time passes at a different rate. So it takes about 8 seconds to reach from the atmosphere to the surface of the Earth. But the lifetime of muons is just 2.2 microseconds. So for us, they are living a life of 8 seconds as they're able to reach from the atmosphere to the surface of the Earth. But actually, lifetime they have is of 2.2 microseconds. So this helps explain the concepts why muons can. Another beautiful example is of future ships. So we know us humans have a lifetime of say 100 years. In 100 years, you can't travel anywhere in space except for some planets in the solar system. So you can't reach any distant galaxies, distant stars with your lifetime. So the example that we could use of time dilation is in future ships. So in future ships, what you could do, if it's possible, you can accelerate the ships at 99% the speed of the light. When you're moving at such high speeds, time will pass slowly for you. So you will be accelerating in space, you will be moving through the space, but time would pass at a slower rate for you. So with this application, you could actually reach stars within your own lifetime. This can be explained by the fact that, but it has a pitfall that I'll explain afterwards. For the people on Earth, time will pass at the normal rate. It will take the normal time, the normal amount of time that you'll take to reach the black hole. For example, take the example of Milky Way galaxy. The Milky Way galaxy is about 1 lakh light years in diameter. 1 lakh light years means that light takes 1 lakh years to travel across the Milky Way. So at such large distances, you can only imagine to reach such places. For example, let's take the nearest star apart from the sun, Proxima Centauri. It's about 4.2 light years away from us, right? So if you travel by the speed of light, it will take you 4.2 light years. So let's say that you travel at the speed of light, which is not possible actually. So let's say that you travel at 90% the speed of light. So it should take you about 4.5 years to reach there, right? But there are also larger distances. For example, the nearest black hole is about 2,000 light years away. So to travel that, you have to live a lifetime of about 2000 years, even if you're traveling at the speed of light. So what you can do here is you can travel at a very high speeding ship. So if you're in that speeding ship, time will pass at a different rate for you. It will pass slowly. You'll age slower. So you can reach that black hole not in 2000 years. It will take you about, say, for example, I haven't really done the calculations. So it will take you about, say, 50 years to reach that black hole. But for here on Earth, about 2000 years had passed. So even if you find a planet where you can survive, or even if you can find a alien life, and if you come back to the Earth, I'm not sure if you'll find life back here on Earth, or we might have even extinct. We might have even gone extinct. So this is another important application. Uh, yeah, so in both these type of time travels, there's a catch. If you travel once into the future, if you use kinetic time dilation or you use gravitational time dilation and you travel into the future, the catch is that you can't come back. It's not actually time travel. You're using the laws of physics to bend time, right? So you can go into the future but you can't come back. So if you had bet on a match or done anything, you can't profit it and come back and say that, oh, I won. So you can only travel into the future. It's just a one-way road. Right. So yeah, so there are many applications of time dilation apart from these. Time dilation corrections are used in GPS satellites. So if time dilation is not taken into account, that if you are at a lower gravitational field or if you're traveling at a higher speed, if that's not taken into account, GPS satellites won't function accurately. For example, that if you are using Google Maps, it will show you about your location from your location would deviate at a rate of 11 kilometers per day. So you might be in Delhi and the next day you might be in Haryana. So GPS satellites won't function properly. It's the same in many satellites and all these things. There are many minute effects of time dilation as well. For example, if you're living in a hilly area, or you're living in a at a higher altitude, so time would pass slowly for you, but it would be at a very negligible rate. There's also an intriguing application. For example, if you are sitting, when you're sitting, you're at a higher gravitational force, very negligibly, but you're at a higher gravitational force as you're closer to the Earth. But when you're standing, you're at a lower gravitational force. So when you're sitting, you actually age slowly as compared to when you're standing. That's a very minute effect, and you should not use it as an excuse to tell your mom to be sitting in front of the TV all day. It does not work out. So this was it. These are a few examples of time travel to the future. In the end, I would just like to say that say something about time travel to the past. Time travel to the past is nearly impossible as it provides a lot of paradoxes. For example, the grandfather's paradox and various paradoxes that prevent the time travel to the past. There are a few ways in which you can time travel to the past. For example, there are space strings, time strings, time loops. So those are very complex physical phenomena. For example, I can try to explain time loops. Let's say, okay, just a second. I'll need a prop. Just a second. Yeah. For example, imagine this string to be the timeline. So this the start would be the past, the middle would be the present, and the end would be the future. So if we live in a rotating universe, so as we know, our universe is not rotating per se, but let's say you're near a rotating black hole. Near a rotating black hole, the environment is very harsh. Probably discuss it in another talk or something. But near a rotating black hole, the space is curved in a very weird way. So example, say that this time string. So we all might know that space is a mixture of space and time. So when there is space, there is time. Space time is the fabric of the universe. So for example, imagine this as the string of time. When the universe curves around it, or when you're near a rotating black hole, these time strings tend to curve. So if they have enough rotational momentum, they'll form a circular loop. So for example, if you start at the past, you should be able to travel into the future, in the present, and then you might be able to travel into the future. But as they have formed a circular loop, you should be able to travel back to the past. So this is a possibility of time travel to the past, the formation of time loops, but it's really hard because it needs a very harsh environment and too many calculations to actually perform. They might happen at a specific point in space. You might not even know. Like there'll just be a point in the universe where these time loops are formed, and you won't even know the difference. There's also another possibility that if you're near a rotating black hole and if you go into an angle, this is similar to a rotate time string. If you go into a specific angle, a calculated mathematical angle, then you enter the rotating black hole and you might enter a time loop that might have formed near a black hole. So if you go into that time loop, you'll come out of the black hole into the past. So it depends on when the black hole would have formed, say 1,000 years, a billion years, many billion years. So you would have come back into the past. But there are many other problems with that too. If you even if you come out of a black hole, there's no saying that you won't go back in, or you won't be able to come back to the earth. You'll just be wandering around near a black hole. So that's it for my talk today on time travel. I hope you all enjoyed it. If you have any other questions, you can let me know.
Siddharth, you could have shared a video also, no? Any relevant video on it?
Yes, ma'am. I didn't find many relevant videos, ma'am. This is something that I gathered from many sources about time travel.
Yes, very well explained. Anyone has any questions?
Thank you, ma'am.
What do you think about multiple universes? Like,
I think that's a fair possibility that we have a multiverse full of infinite universes. Quantum mechanics also explains the possibility of a multiple universes based on
yes,
probability.
it does.
Yeah, based
But
on
then,
yeah.
so at one point, one of us would be doing something, and that
Yeah.
in the other universe, some
Yeah.
other person would be just similar to us, but yeah, it could be different. We have even seen it in movies recently.
Yeah. So
You
quantum
have
theory.
you have watched Marvel, right?
Yeah, a lot.
Yeah. So that's how you could have infinite deviations from the timeline, and that could be
Yeah.
a possibility actually at some point.
Yeah. So at each point in life, everyone takes a different decision. So in another multiverse, in a universe out of the infinite in the multiverse, some of one doppelganger of us might be taking the wrong decision.
Yes,
So
so yes, and in fact, if we look at the grandfather's paradox, if we go into the past, so for example, if we go into the past and even make a slight change, so that can actually affect the events, the following events, and that can actually disturb everyone.
yeah, and the infinite universe.
See, I think in a grandfather paradox, a new timeline can be formed and it practically won't be a paradox because if it affects any recurrence, future events, then a whole timeline will be formed, a new timeline. So I don't think it can be a whole paradox. I have that question a few times.
Yeah, but we don't know if there's something that how the timeline would change. Can you explain how the timeline would change? We don't have any phenomena or any physical process that we can use to say that the timeline would change. So it's not that there's a some that like there's in the Marvel there was a time variance authority. So there
Yes,
are not there are no such things in our universe as that we know of. So the timeline might not change. So that paradox is
yes,
there.
and there is no citadel at the end of time, and there's
Yeah,
nothing, no one controlling it actually.
yeah, it's just based on probability. You
Yes.
So there will be a universe where so if there are infinite universes, there will be an infinite amount of tejasis, infinite adityas, infinite siddharth. So they're based on probability. So when you take a decision in this universe, in one of the infinite universes, someone will take the opposite decision. So by probability, there will be one universe where the siddharth will take all the wrong decisions and would be leading a miserable life.
But then that decision can also affect others, and gradually it would create a sort of a chaos.
Yeah, yeah. Any other questions?
But if we saw in the movie, if the whole world is getting destroyed, for example, when Loki and Sylvie, when they went to that planet where everything was getting destroyed, I forgot the name. So if you actually make a change there at a specific point, then there's no deviation
Yeah,
that
because
was observed.
as seen in the movie, it's called as the end of time, or there's nothing
Yes,
after it. We don't have any such end of time. For us, time is infinite. So
yes,
that
yes.
that place is called as the end of time. So if you change something at the end of a line, say for example, if you remove a person at the end of the line, the whole line does not change. The position of all the people remains.
Yes, it will be.
Yeah, so that's why there's no change if you do anything there. Any other questions or ideas, anything?
Ganeev, Ayush, any questions? Do you want to participate in some discussions?
Ayush, are you there? Ganeev, are you there?
Yes.
To ask anything?
No.
Ayush, any questions?
No.
Aditya?
No, no such questions.
Okay, then. Good job done, Siddharth. I
Thank you,
really
ma'am.
hope we could have found any relevant video also to show them.
Yes, ma'am. I'll look into it, and if I find a
Have you
video,
seen that YouTube channel, Minute Physics?
yeah,
That is good. So maybe it's there. Something related.
I'll look for a video. Actually, I know a professor called as Professor Ron Mallet. He works on time travel. So I'll see if there's any lecture or any video that I might find that will be intriguing. So I'll share it in the group or in the next presentation.